Hi guys. Alright, today we're going to learn about Riemann sums, summation notation, and the definite integral. So the sums in which we'll be interested are called Riemann sums, named after George Frederick Bernard Riemann. LRAM, MRAM, and RRAM that we've already learned are all examples of Riemann sums, not because they estimated area, but because they were made in a certain way. We're now going to describe the construction formally of how you can make a Riemann sum. So we have to have a function f, and I've given you a graph of function f, this little blue curve here, that's f of x, okay? Now delta x may be different. Notice this width here of this rectangle, and then this rectangle is wider, and this one is skinny. This one is even wider. They all have different bases. The delta x's are different, and that's okay. What happens is we're partitioning it at x0, x1, x2, all the way down to xn. They're telling us where to partition it, what x values we're going to use to partition. Now, the c values here, these c values are also x values, but these are the x values we're going to use to find the heights of the rectangle. So you can see in the first rectangle, the left endpoint was used. In the second rectangle, it looks like the midpoint was used to find the height. And it might be the midpoint in the third one also. But notice in the fourth one, it's just this random x value there. Okay, it doesn't matter, and you can see in the last one, it's just some random x value in that subinterval that was used to find the height. It does not matter. Now remember, when we do this, we find the areas of the rectangle. Now to find the area of a rectangle, it's the length of the base, which is delta x, times the height of the rectangle, which is the function value evaluated at the c's. Okay, so that's c sub k, that's I used this c, then I used this c, okay, which c values are used for each rectangle. And we add up, that's the sum. We add up all those areas, and that's called a Riemann sum. Now it's a Riemann sum, not the Riemann sum, because there are many, many possibilities. There are an infinite number of ways you can break up the entire interval. There's infinite number of ways that you can then choose x values in each subinterval. So there's lots of ways this can happen. Okay, there's lots of different Riemann sums. Let's look at one that's not an LRAM or an RRAM or an MRAM, and let's find the Riemann sum. So here's the graph of the function. F of x is the square root of x. Now we're going to partition it at 0, 2, 3, 5, 8, and 9. That means we're going to have a rectangle going from 0 to 2, 2 to 3, 3 to 5, 5 to 8, and 8 to 9. Notice from 0 to 2, our delta x is 2. From 2 to 3, our delta x is 1. From 3 to 5, our delta x is 2. From 5 to 8, our delta x is 3. And from 8 to 9, our delta x is 1. Okay, those are the bases of these rectangles. That we will draw. We haven't drawn them yet. Okay. Now, we're going to find a Riemann sum using these x values to find the heights. We're going to use these to find the heights. So those are the x values that we're going to substitute into the function. So I'm going to write this a little weird. The area from 0 to 9 is approximately, now our base of the first rectangle is 2 times f of, we're supposed to use 1 to find the height of the first rectangle. So now let's draw this. Here's 1. I'm going to come up to the function. Now I'm going to go to the left and to the right, and then I'm going to come down to the endpoints of the subinterval. Then we're going to do our next rectangle. From 2 to 3, that delta x is 1. F of, now we're supposed to use 2 to find the height. So we're going to start at 2, go up to the curve, come over to the end of the subinterval at 3, then come down, and we're going to use the area of that rectangle. Now the next rectangle from 3 to 5 has a base of 2 times f of, we're supposed to use 4 to find the height. Notice 4 is between 3 and 5. Now I'm going to use 4. I'm going to go up and find the height. I'm going to go back to 3, over to 5, come all the way down. There's my rectangle. Now my next rectangle goes from 5 to 8 and has a base of 3. And this time we're supposed to use 6 to find the height. So I'm going to go from 6 straight up to the curve. I'm going to go back to the beginning and then over to the end, which is all the way at 8. And I'm going to come down so I have my widest rectangle there. And the last rectangle is only from 8 to 9, which has a delta x of 1. And this time we're supposed to use 9 to find the height. So from 9, I'm going to go all the way up to the curve. I'm going to come back to where x is 8. And then I'm going to come down to finish my rectangle. Okay, so now we have the picture drawn. So now we have to do some computations. Now remember, f of x is the square root of x. So it's 2 times the square root of 1, which is 1, plus 1 times the square root of 2 is rad 2, plus 2 times the square root of 4 is 2, plus 3 times the square root of 6 is rad 6, plus 1 times the square root of 9 is 3. Now we've got 2 times 1 is just 2. So 2 plus 3 is 5. Plus a rad 2 plus 2 times 2 is 4 plus 3 rad 6. We're actually looking at 9 plus radical 2 plus 3 rad 6. So this is the exact value. Now if we put this in our calculator, we will get approximately 17.763. And that's the area under the curve. Woohoo! Okay, now we want to find a Riemann sum for f of x is sine pi x on the interval from 0 to 3 pi over 2. We're going to use partitions from 0 to 1/2. That's a delta x of a half. 1/2 to 1 is a delta x of 1/2. And from 1 to 3/2 is a delta x of 1/2. Nice, they all have the same delta x this time. And we're going to use C1 as 1/4, C2 as 1/2, and C3 as 3/2 to find the heights of each of these rectangles. So this time, we're going to have our Riemann sum. I'm going to be formal here. The summation is k goes from 1 to 3, because we have 3 rectangles, of f of c sub k times delta x sub k equals, now our first rectangle, the delta x is 1/2, f of, we're going to use 1/4 to find the height the first time, plus delta x is still 1/2, and in the second rectangle, we're supposed to use 1/2 to find the height, plus our delta x is still 1/2, but in the third rectangle, we're supposed to use 3/2 to find our height. So that gives me 1/2. Now remember, f of x is sine pi times x, so this is the sine of pi over 4, plus 1/2 times the sine of pi over 2, plus 1/2 times the sine of 3 pi over 2. And of course we have these values memorized, don't we, guys? 1/2 times the square root of 2 over 2, plus 1/2 the sine of pi over 2 is 1, plus 1/2 the sine of 3 pi over 2 is -1. So these are going to add to 0, and all we have is radical 2 over 4, which is approximately 0.354. And that is our answer. Ta-da! Now, does that represent the area under the curve? You might want to think about that and start wondering what's going on, because the answer to that question is no. I wonder why. We've been doing area under a curve. That sounds weird then. There's another term we need to introduce here. The norm of a partition, and it looks like a double absolute value. That's what it is. It looks like a double absolute value symbol. So that's read the norm of the partition P. Okay, the norm of the partition P is the longest subinterval in P. It's the length of the longest subinterval. So, for instance, let's find the norm in the first example. So we want the norm of the partition. So we want to go back to example 1. Here it is. We had delta x is 2, 1, 2, 3, and 1. This is our longest subinterval. So the norm of the partition, the longest subinterval, was 3. That's it. It's the biggest delta x. That's all it is, okay? Now, we need that terminology because what happens if we take the limit as the norm of the partitions get to 0? So the longest, the biggest partitions, the biggest intervals are headed to 0. Everything's heading to 0. They have smaller and smaller and smaller subintervals, okay? That means more and more and more and more rectangles. That should be getting closer and closer to the actual sum. And if that limit exists, this limit of the norm of the partition of the Riemann sum, remember all this is our formula for the Riemann sum. This is what we call the integral from a to b of f of x dx. And it's amazing because you get the same limit regardless of what partition you use and what values of x you use to find the height. It does not matter. Now, this integral from a to b of f of x dx is called the definite integral. Now, it's a definite integral because it has numbers where the a and the b are. If there's no numbers there, then it would be the indefinite integral, okay? And there's a theorem that says if a function f of x is continuous, continuity is so important, on a closed interval from a to b, then the integral from a to b of f of x exists. And that theorem was proved by George Riemann back in 1854. So let's examine this definite integral. Okay, now Newton and Leibniz discovered calculus separately around the same time. We tend to use Leibniz's notation, okay, the Greek letters of summation, which is what we were using before, the limits of the summations, become the Roman letters once we've taken the limit. So that's where this integral symbol comes from. So the notation here is read as the definite integral from a to b of f of x with respect to x. So the integral is that swirly figure from a to b of f of x, and the dx is telling you with respect to x. That dx is the change in x. That's our old delta x, okay? So let's look at this again. So we have here, this is our integral sign. Then we have our upper limit of integration, and we have our lower limit of integration. We have the integrand. The f of x is the integrand. What are you taking the integral of? And then the dx is telling us that x is the variable of integration. And the whole thing together is the definite integral from a to b. And when you find the value of the integral, you have evaluated the integral, okay? Now, we're going to express, and we're going to start with some easy ones. We're going to express the limits as definite integrals. So here's the limit of the norm of the partition heads to 0 of the summation as k goes from 1 to n of 2c sub k cubed delta x sub k. So now remember, when we write this as an integral, we go from a to b, and that's the length of our intervals. So the integral from -1 to 0. We need to find f of x. The delta x, remember, is our dx. Everything else here, 2c sub k cubed, that's part of the f of x, but they plugged in c sub k. So the function was 2x cubed. Every place there's a c sub k, remember your c sub k are all the different x values, okay? And then the delta x becomes your dx. That's it, right? The integral notation is much simpler. Look at b. The limit of the norm of the partition heads to 0 of the summation as k goes from 1 to n of the square root of 2 minus c sub k squared times delta x sub k, where p is a partition of the interval from 0 to 1. So we're going to write the integral. We're going from 0 to 1. Okay, this is my delta x, is my dx. And then my function, I have the square root of 2 minus, but instead of c sub k, we put x squared. There you go. That's that. That's it. Now, a little note here. If f of x is non-negative, notice it says non-negative. That means positive or 0. Then the actual area from a to b is the integral from a to b of f of x dx. That's pretty cool, right? We were doing that for the most part. But notice it says non-negative. So what happens when f of x is negative? Let's see if we can figure this out. So the first thing I want to do is I want you to use your Riemann sums program, and we're going to approximate the area under the curve f of x equals sine x from 0 to pi using 10 subintervals. Let's go get that. So here we are back in the Riemann sums document. We're going to come over here to our f of x, and we're going to change this function to sine x. Now sine only goes up to 1, so let's make this like 1.5. Around 2 pi is about 6.2, so let's just say we'll go to 7. Negative 1.5 again. Negative 1.5. And then negative 0.5. Okay. And we want to go from 0, so I'm going to slide my a to 0, and I'm going to bring my b. Now, it's really hard to find b as 3 on this one is 3 or 3.5. Okay? You can do this with it, and what are we going to have? We're going to have, so we'll have to approximate here, but 10 subintervals. Now, we're not quite because we have this. Now, I'm going to open a document that you don't have, but hold that thought. So this one is set up to deal with trig functions. It's the same idea, it's just slightly different, but it's set up to deal with the sine, okay? And we've got a at 0, b is at 3.14, and we want n to be 10. So no, oh, there's my, oh, look at that. There's my n is 10 right there. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. My LRAM is 1.98. My R is 1.98. And my M is 1.96. Okay, so it gets really close. Now those are approximations. Okay, we can, of course, increase n. And the closer, the more we do that, the better our fit will get. But it'd be really, really cool if there was a program where we could do this with thousands of subintervals, right? Thousands and thousands of subintervals. Well, your calculator actually has a built-in program. It's on our template key. And it is found at the end here. It looks like an integral from box to box of box to box. That is our integral setup. So we're going to go from 0, and we're going to tab to pi. And then we're going to tab, and we're going to put in our trig function, sine of x, close the parentheses, tab, dx, and we hit enter, and we get the value 2. Awesome. Okay, now that was from 0 to pi. And if we look at that graph, so from 0 to pi, we got an area of 2. What do you think the area from 0 to 2 pi is? What do you think that area is going to be? 4, right? Makes sense, because if you look at that graph, this area looks the same as this. So if this is 2, then this is 2. It should add up to 4, right? Let's check it. We'll use our template key, and we go from 0, tab, 2, pi, tab. Get our trig function, sine of x, close it, tab dx, enter. What the heck? We got a warning sign which says something's wrong. Notice it's in scientific notation. This is 14 zeros, 0.000000, 14 zeros, then 3, 4, 5, 6. Do you know what the calculator is trying to tell you? The calculator is trying to say 0. The calculator thinks the area is 0. Let's go back to our notes. Okay, we saw on the calculator that this area is 2, and we expected the area from 0 to 2 pi to be 4. But we got a 0. The reason that is yes, the physical area above the x-axis is the same as the physical area below. So the total area is 4, okay? But the integral does not give us that. So the total area is 4, okay? But if f of x is negative, then the area is the negation of a to b of f of x dx. The integral gives us signed area, okay? So the top part, it gives an area of 2, and the bottom part, the integral is giving an area of negative 2, which is why when it adds it together, we get 0. Kind of weird. So for instance, another way to say that is that the definite integral from a to b gives us net area, okay? It gives us net area. For instance, if we have a graph that looks like this, and this is on the region from A to B, let's say it intersects here at C and intersects here at D. This region from A to C, the integral is going to have a positive value. This region between C and D, the integral is going to give us a negative value. And again, when we're up here above the x-axis between D and B, the integral is going to give us a positive area. So this is what I mean by signed area. Area is supposed to always be positive, but the integral makes it positive and negative. Now that means we have something called net area. So the net area, when we have the integral from a to b of f of x dx, what we do is we find the area above the x-axis minus the area below the x-axis. Because the area above the axis is positive, the area below the x-axis is negative, so the net area we take above minus below. So at times we're going to integrate functions that go below the x-axis that have negative values. And here's a few pointers. Area below the x-axis counts as negative area, and the total area between A and B for some curves is really a net area, where the total area below the x-axis and above the curve is subtracted from the total area above the x-axis and below the curve. So it's really important for us to remember that the definite integral gives us a number that calculates the net area, not necessarily the actual area. So the actual area between the curve and the x-axis is not what the integral finds. Something to keep in mind is that if f of x is greater than 0, that means that the graph is above the x-axis. Then the integral from a to b of f of x dx will give us the exact area. However, if f of x is less than 0, which means that the graph is below the x-axis, then the integral from a to b of f of x dx will give us the negation of the exact area. And then if we have a function that is both positive and negative, we're going to have to break up the integral into regions where the area is positive, regions where the area is going to be negative, so that we can compute this net area. Okay, guys, we've done enough for now. I will see you tomorrow. I hope you all have a wonderful day. Bye.